Okay, folks, in this very quick video, I will make additional comments in relation to these two objects, directional derivative and gradient. Okay, so we know with you the following fact. If I have a vector in Rn, and that's a unital vector, then we have this formula for computing the directional derivative. It's not working every time, but it works most of the time, and let's just focus on these nice cases, so when we can use this formula. So the formula says that directional derivative in the direction of u, or rate of change in the direction of u, is given by the following dot product. Okay, it's a gradient dot product with the vector u, normalized vector u. Now, what I would like to remind you from your past knowledge of dot products is that for the dot product there is such geometrical formula which says dot product always equals to product of magnitudes of these two vectors times the cosine of the angle between these two vectors. So theta here is the angle between the vector gradient of v and the vector u. Now in our context, use unital, so this factor just disappears and we end up having just this. Alright, and this value of this formula for the rate of change, it allows you the following interpretation. In fact, cos, we know that the cos function never exceeds 1 or minus 1, or in absolute value it never exceeds 1, and that gives you this relation. That the rate of change in the direction of u, no matter where this direction points, will never exceed the magnitude of the gradient. Rate of change in any direction, regardless of the direction, will never exceed the magnitude of the gradient in absolute value. Or if you would like to present this without absolute value, then the rate of change is always bigger than negative, the magnitude of the gradient, and less or equal than the magnitude of the gradient. Furthermore, if it happens that your cos is exactly 1, which means that these two vectors are parallel, then your rate of change will be exactly the magnitude of the gradient. So this right-hand side inequality will become the sharp equality. And that's what we call the fastest rate of change, or the fastest growth, and the direction of that fastest growth. So the result which you have to remember is that any function where this formula is applicable has the fastest rate of change in the direction of the gradient. In the direction, so that's what I'm saying here, the fastest rate of change of any function at any point is always the magnitude of the gradient and is always in the direction of the gradient. And the fastest decay, or negative rate of change, will be in the opposite direction to the gradient. The fastest decay of your function will be negative the magnitude of the gradient, and that will happen in the direction of, in fact, in the direction opposite to the direction of the gradient. That's the second fact which you have to remember when you connect these two objects via this formula. And the third fact, which is also very worth remembering, is that if it happens that your direction u is perpendicular to the gradient, which means this angle is 90 degrees of pi on 2, and the cos is 0, your rate of change in that direction is 0. So any function doesn't change in a direction perpendicular to the gradient.